So welcome to today's session. We are going to go through OCaml Functors. So in this tutorial, we look at how to apply functors and how to write functors. We'll also see some use cases involving functors. So what is a functor? Functor is like a function, whereas functions are between values, functors are between modules. Functor can take a module as a parameter and can return a new module as a result. So where is this useful? So in cases like you want to extend an existing module, or you want to stub specific functionality to do testing, for example, right? Or you want to do dependency injection. So those are cases where functors are quite useful. So let's start with an example here. So in this tutorial, we're going to create a new project called funct. So let me just make a directory for functors, and we're going to create a directory called funct. Go into funct, we create the Dune project file using plan Dune 3.7, and we're calling the package name funct, and then the file is funct, public name is funct, and we're going to use the str library. Then we'll create one empty file called func.ml. Let's try to run this. OCaml exec Dune funct. Let's try this again. I do the correct name here for Dune? Name funct, public name funct, libraries str. That looks fine. Thanks Privan, I forgot the exec. Open exec hyphen Dune. Oh, great, thanks. So that doesn't do anything, but it should not fail either, right? So maybe I will reduce the font size so I can see the whole line. Right, so now let's continue. So the standard library contains a set module which is designed to handle sets. So this module enables you to perform operations such as union, intersection and difference on sets. Okay, there's a separate set tutorial which you can go on to later. Now to create a set module for a given element type, it's necessary to use the set.make provided by the set module. So as a functor, you take in a module and you return a new module. Welcome user bin cat. Yes, we are going through functors today. Right, so to create a module for a given element type, so use the functor set.make provided by the set module, and a simplified version of the sets interface looks like this, right? It's a type T and a compare function, and here you call module make functor of ordered type to set s. So what it does is, like a function, the functor set.make, it takes a module of type ordered type and returns a module with signature set.s. This is this one here. and the module type auto type requires a type t and a function to compare, which are used to compare between the elements of the set. Yeah, I would suggest going through from the original videos. I have a playlist. I'll share the link in the chat, so you can go through the OCaml playlist, and then I start with the tour of OCaml, then go through values, functions, data types, and so on. So I would encourage you to go through that.
Sura Guide 12ஆம் வகுப்பு பொதுத் தேர்வுக்கான புதிய பதிப்பு.
I'll share the link
மாணவர்கள் பொதுத் தேர்வில் அதிக மதிப்பெண்
playlist at in the chat as well. So you can watch the previous videos as well. Alright, so let's continue here. So most set operations need to compare elements to check if they are the same, right? To allow a user-defined comparison algorithm, the set.make functor takes a module that specifies both the element type t and the compare function. So passing the comparison function as a higher order parameter would be a lot of boilerplate code. So set operations provide a functor which allows you to specify the comparison function only once. So here's an example. Let's try this. So we do, let's call it module string compare struct type t string, let compare string dot compare end module string set dot make of string compare. Okay, so this defines a module funct dot string set, right? We're still in the funct module, and what set dot make requires is a type t, which is here string, and a function to compare. We're just using the string dot compare here. Let's see if this compiles fine. Okay, no errors there. So this can also be simplified using an anonymous module expression, right? So I can say, write this as string set directly as set dot make of struct type t string, let compare string dot compare end. I close this. I don't need this here. A simplified version. Let's check that compiles fine. That looks good. So the module struct to end is inlined in the set dot make call. Since this string module already defines the type t, which is an alias for string, and has a compare of type t, takes a t and the 2t and returns a bool, comparison of two strings. We can further simplify this. So we can just say module string set is set dot make of string. Let's compile this again. That looks fine. Okay. So the module resulting from the functor application set dot make is bound to string set, and it has the signature set dot s, and it provides the operations on the set of strings. Okay, the function string dot compare is used internally by string set. Now, of course, when you ran this, it doesn't do much. So we can actually add some code to use this. Let's use this module. I'm going to say let in channel input lines pipe it to list concatenate map split regex slash t dot comma semicolon colon parenthesis plus, right, and then type it to string set of list called string set dot iter print end line. Hope I've not made any mistakes there. So what it does, in channel input lines reads lines from standard input, concat map splits the lines into words and produces a word list. String set of list converts the word list into a set, okay, and iter displays the set elements. Okay. So the functions of list and iter are available in the functors application result. So let's try it on the Dune file itself. So this is the Dune file. So if I do OCaml exec Dune exec func less than Dune, there's a typo. RegXP, I missed the P. The joy of live coding. It compiles and it outputs the results, right? Good. So there are no duplicates in this set, so therefore funct is displayed only once, although it appears twice in the Dune file. Now we can extend a module with the standard library functor. So the way to do it is using the include statement. So there's another way in which we can actually write this func.ml. So here we can say module string struct end. Here we just say include string, and we can say module set dot make of string. We don't need this. Here we stdin, we pass it in channel input lines, and list concatenate map string dot split xp, right, and then we call string dot set, because we're having this module called string here, right, and inside the string we have set, so string dot set of list, and then string dot set iter. Okay, let's compile and run this, and we get the same output. That's good. So this is a way of extending a module by trying to include a standard library functor. Now we can parameterize these modules with functors. So a functor is almost a module, except that it needs to be applied to a module. Okay, so this turns it into a module, and thus functor also allows module parameterization. Now the same for the sets, maps and hash tables that are provided in the standard library. Once we finish this section, we will go through the other examples, the other data structures as well. So it works like a contract between the functor and the developer. So if you provide a module that implements what is expected, it is described by the parameter interface, and the functor will return that module that implements what is promised. Okay. So here's an example of the module's signature that the functor set.make and map.make expect. Okay. And this is for example of the functor hashtable.make. There's a type t, there's an equal function and a hash function. So the functors set.make, map.make, hashtable.make return modules satisfying the interfaces for set.s, map.s, hashtable.s respectively, which also contain abstract type and associated functions. User-driven caching very similar to chaining functions. Yeah. So let's see how to write your own functors. So one reason to write a functor is to provide a data structure that is parameterized. The same thing as the set and map and other data structures that we have seen. So in this example, we are going to take heaps data structure. Now there are different types of heaps, right? You can have binary heaps, leftist heaps, binomial heaps, or Fibonacci heaps. Now we're not going to go in detail into each one of these heaps, but we're going to try and implement this and using a parameter. Okay, so an example looks like this here. So it's the element type check is empty. You want to insert into the heap, you want to merge the heap, you want to find an element in the heap, you want to delete an element in the heap, and so on. So heap implementations can be represented as functors from ordered type and heap type, and each kind of heap would be a different functor. Okay. So with functors you can also have like module states. You can have multiple modules with different states. Okay, that's kind of useful here. So let's look at an example of heap.ml. So same order type, module type with all the types and elements. Then we're looking here example as a binary heap. Okay. But you can extend this by adding one more functor for say heap.leftist, heap.binomial, and heap.Fibonacci, and so on. Now the other use for functors is dependency injection between modules. So here is a example of func.ml. It embeds an additional iterprint module but exposes a single function of type string list unit, and it has got two dependencies: module list through list.iter and module out channel through out channel.output string. Okay, so let's try to write this. Let's update func.ml. So you say module string set dot make of string. We have module iterprint signature string list to unit and struct let f list dot iter func s out channel output string std out s concatenate with /n. Okay. And then we call end. Then we do stdin in channel input lines, list concatenate map string split regular expression. It's fine. Then we call string set of list. Then we have string set elements, and then we call our new iterprint.f. Hopefully I have not made any typos here. Let's try to run this. Then dune set dot, oh, it should be capital M. I'm not using any editor with like auto completion, and so later on you will look at customizing your editors for the environment. So now it runs fine now. Good. So dependency injection is a way to parameterize over a dependency. Okay. We can also refactor this module like this. We have a module type iterable, a module type s, and then we have the module make. So the iterprint is refactored now here. It takes a module providing the function iter as a parameter. Okay, this one. The with type constraint means the type from the parameter replaces the type in the resultant module. This is this one, right? This allows f's type to use dep's t type. So with this refactoring, we have iterprint only has one dependency. So at compilation time, no implementation of function iter is available yet. Now we have gone through the MLI files before. There must be a module. An OCaml interface must be a module, not a functor. Functors must be embedded inside modules. User print cat saying using nano. So yeah, the idea for me is to like first teach the basic like concepts, go through the syntax, semantics of the language, right? You don't want to be stuck in a specific environment or an editor setting and so on. So yeah, I'm also streaming on Emacs. Later on I'll show how to set up Emacs for OCaml development, and then we can have a lot of these auto completion and checking all of that. But I think when you're learning the language, it's good to make mistakes, so you know like how to correct them and what's going wrong, and is there a typo or the syntax error and so on. And we should not be afraid to see those mistakes, right? Only when you see those mistakes you learn from them. So that's why I'm starting with very basic, no customization setup. Good. So with this change, we can update func.module to use these modules set and iterprint, and we should get the same result. So here the dependency list is injected when compiling the func module. That's what is demonstrated here. Now replacing the implementation of iter inside iter list print is no longer refactoring. It's another functor application with another dependency, right? Like say replacing array with list, for example. Right? We're here using array here. Again, if you run this, you should be able to get the same result. Now the modules received and returned by iterprint make both have type t. The use of with type constraint exposes the two types at the same time. This makes functions from the injected dependency and result module use the exact same type. So the type check works fine. When the parameters contain type is not exposed by the result module, the with type constraint is not necessary. So let's look at the naming and scoping here. So the with type constraint unifies the types with a functors, parameter and result modules. So we could have defined iter.make as follows, right? Here the function f is not used, and when we try this, the compilation actually fails. Since make is invoked to create module iterprint, but f is not used, right? So now the type constraint using with type isn't shadowed by definitions within the functor body. So we can redefine this make as follows. The t from with type takes precedence over the local type here, which only has a local scope. So it's good to not shadow names too often, because it sometimes makes the code harder to understand. That's just a simplification. Now we can also write functors to extend modules, right? So say we extend list and array modules with a function called scanLeft. I mean, it does the same thing as foldLeft, except that you want to return intermediate values without changing the original implementation. So sort of writing a functor to extend the module. So let's try this example. So I'm just going to create a directory called scanLeft. We'll create the Dune project, lang Dune 3.7. Let's do Dune library name scanLeft. Let's create the scanleft.ml file. So we have module type left foldable signature has type T. We have a fold left. Now I'm intentionally typing this so that I want you to try this rather than just copy pasting from the browser, so that it sort of registers on what the types are, and also like any syntax errors we can appreciate the compiler for it. So scan left B function, so the B takes A, turns B type, right? In this we have a module, it's left foldable with type f dot struct, and then we define scan left fbu fbua, let b prime is fba in, b prime or b prime u in, say u fold f dot fold left of f to second to list dot reverse to f dot off list. Okay. So what the tutorial suggests is to just run dune utop, right? Let's do that. There's a typo again. Line 5, val of list, can you spot the error? 80 fold left colon B to A to B to B 80 val of list A list to 80 end signature 80 val scan left B to A to B 80 and BT. What will make F left foldable S with type equal to struct scan left FPU FPA in U in U F dot fold left FB second list rev F dot off list. That looks fine to me. Oh, signature. Right. That should compile. Now we are on utop. Now once we are inside utop, we can call array struct. I'm including std lib dot array and then including scan left dot make std lib dot array and calling end. Okay, we get all the functions there. Then we do, let me clear the screen, module list struct, we include the list, we include our scan left dot make now struct, we include the list, let off list function id, and we call end. That looks fine. Now we can define array init 10 elements id array dot scan left plus 0, right? Then you say list init 10 function id list dot scan left plus 0. So we get those intermediate values. So we have extended the array and list to do a scan left where it actually prints the intermediate values. So good example of extending with functors. Now modules can also hold state, right? So functors provide a means by which to initialize stateful modules. This is an example of a random number generation seed. So let's try this. Going to exit from utop and let's create random.ml module type seed type signature int array module type yes signature reset state unit to unit have bits is unit to int val bits 32 is unit to int 32 bits 64 is unit to int 64 native bits is unit to native int is int to int 32 is int 32 to int 32 int 64 is int 64 to int 64 val native int is native int to native int val full int is int to int val float is float to float val bool is unit to bool. Okay. Yeah, I think this one module type, this one should be actually equal to, there is a typo in the documentation. Maybe you can send a PR to fix this one. This is a syntax. Then we do module make, of course, seed type. Yes is struct. Let state is seed dot v random dot state dot make. Reference let reset state is state is equal to random state dot make seed dot v and initial using the initial seed to reset the state. Let bits will be random state dot bits state. Let's bits 32 equal to random state dot bits 32 of state. Bits 64 random state dot bits 64 state. Let native bits random state dot native bits state. Let int is random state dot int of state. Int 32 is random dot state int 32 of state. Let int 64 is random dot state int 64 dot state. Native int is random state native int state. Full int is random state full int state. Float state bool random state bool state end. Let's see if so the tutorial asks us to use utop, so let's just use utop and I can directly load the file using mod use random.ml. Okay, there are no typos there, it is good. So let's instantiate R1 module random.make struct let v is 0, 1, 2, 3, n, right, and then we have another module R2 instantiate with the same values. Okay. Now if I call R1 dot bits, okay, I get this number 7578313889, and if I call R2 dot bits, I get the same value. So it's the initial state. That's what we started off with, right? Now if I do R1 dot bits again, now I get a different value. Now I'm going to reset the state for R1. Right. Now if I check R2, I get the next value in the sequence. This has not been reset, right? But if I do R1 dot bits, now I get the initial starting value, right? So you have like different states in the modules. That is what is explained here. So functor application works the same way as function application, passing parameters and getting results. The difference here is that we are passing modules instead of values. Okay, so that's a very quick overview of what functors can do. So I will make this video available on my YouTube channel, and also the quick reference notes. I will push it to the Stitch repo, which I'll also share in the chat. Please try this on your system and let me know if you faced any issues. Since we have covered functors, we can actually go and check the other data structures in the learn module section. So we'll continue with that in the next sessions. Thanks for joining, and hope it was useful. I'll see you in the next week.